So what I want to do today is not go over new material or anything like that. I do want to finish a thought, and especially to deal with the one part of 4.1 that I have not discussed in class, but I did assign you in reading. So let me just back up, and this is kind of a part of the review. If you asked me to summarize the first 9 weeks of this class in a single sentence, so I could put it on a t-shirt, that sentence would be: positive feedback creates bistable switches. Positive feedback creates bistable switches. Make that into a t-shirt, but burn that into your DNA. Absolutely get clear on that, because you see, if you understand the phrase bistable switches, that means you understand equilibrium points. You understand stable and unstable equilibrium points, because you know what a switch is, and you know what a bistable system is. It's two stable equilibria flanking an unstable equilibrium, also called the threshold. Just unpacking that single sentence would cover a lot of the first 9 weeks of the class. And then you saw lots of examples of bistable switches, commitment to maturation in oocytes as a function of progesterone, commitment to adipocyte, the lac operon, the allele effect, all of them are bistable switches, and all of them have some positive feedback. So that's wonderful. That's the first 9 weeks of the class. Now we draw a big line, and we say we're going on to something completely different. And that completely different thing is negative feedback. And can I summarize this week and the next 3 weeks of LS30B in a single sentence? And the answer is yes, I can summarize anything in a single sentence. Can I summarize that in a single sentence? The answer is yes. And it would be: negative feedback creates oscillations. And that's, if you could speak at length on those two subjects, you would have mastered LS30A and the first half of LS30B. That's it. These are the two slogans that I think are the most powerful lessons that I'm trying to get across. So along the lines of negative feedback produces oscillations, because that's what we're now talking about, we have to review very quickly, what do we mean by negative feedback? Because remember, positive feedback, when we talk about positive feedback, it was either X increases X, or maybe X increases Y and Y increases X. And those are two cases of positive feedback. Now, negative feedback actually has two different flavors. The first flavor is when either X actually decreases X, or maybe X increases Y and Y decreases x. And by decreases, I mean makes x go down. So an example of that kind of negative feedback is a thermostat connected to an HVAC system. And I say HVAC because you got to have both heating and air conditioning. So what does the thermostat do if the temperature is too high? It turns on the air conditioning, and the air conditioning actually makes the temperature go down. The negative. If it's too cold, it puts out heat, and heat actually makes the temperature go up. But then I said in biology, there's a second kind of negative feedback, which is much more common. And in that case, we can't make x go down because there's no capability. X is a hormone level in your body. The only way we can make x go down is by metabolizing it or excreting it or doing something like that. That's perfectly good. But the kind of negative feedback that we see in biology is more like the case where we don't have an air conditioner. All we have is a heater. And the heater is going to put out heat. And the question is, how much heat is it going to put out? And you're going to have a thermostat on that heater. And the only thing the thermostat can do is tell the heater to put out less heat. Because it's a heater. It can't cool. So it can only put out heat, and therefore your control of it is simply to say, put out less heat. It's all positive, but you're saying put out less positive rather than more positive. That's what happens in biology. And what that's saying is, if there's negative feedback of X on Y, and we have this biological case, then what that's saying is it's never going to be negative.
He's so cute. He's so cute.
And the bigger the X is, that's going to have the effect of decreasing the, so to speak, the amount of heat that the heater is putting out. So if the temperature is very low here, the heater puts out a lot of heat. If the temperature is very high over here, the heater puts out very little or zero heat. But that's all you have. So that's very typical of the situation in biology, and it's just two different kinds of negative feedback. And this one, this one is the one that we're going to focus on a lot because this is what happens in biology. And we're going to try to model that. So now we have to model that. And here is X and here is Y. And here is this downgoing sigmoid, which is going to model our negative feedback. And then the whole question is, okay, that's a nice shape, Alan. What's the equation? Yes.
No, it's just us talking about muting the mic. Sorry.
Oh, I see. Okay.
I said I'll pass on any questions. Don't worry about it.
Oh, okay.
Good. Oh, wonderful. You're going to pass on questions?
Yeah.
Good. So we have this downward going sigmoid. It represents exactly what we want, and all we need is the equation. And we go to the math department and we say, what do you have that looks like that? And they say, oh, ma'am, absolutely, coming up, we have 1 over 1 plus x to the n. Notice that when x is 0, it has its maximum value, which is 1. And that as x gets bigger and bigger, this expression gets smaller and smaller, which is exactly what we wanted. So remember, upgoing sigmoid is x to the n over 1 plus x to the n, and downgoing sigmoid is 1 over 1 plus x to the n. And just like with the upward going sigmoid, the n modulates the steepness of the curve. So when we have a nice figure of this in the book, when n equals 2, the curve looks like this. When n equals 5, the curve starts to get steeper. And when n equals 10, it's very steep. So what we are modeling here, so increasing n causes an increase in steepness. And what is steepness of this curve? As long as we're having a review, the people who were in my office an hour ago were asking about sensitivity. What is sensitivity? And we said sensitivity is the steepness of the response curve. It's the output, the input. The slope of that sensitivity. So notice that increasing n increases the sensitivity of the feedback. If you have a very gentle, like that blue curve, which is very gentle, then as x increases, y decreases gradually. So in the case of the red curve, as x increases, once you get into that middle region, a little bit of change in x gives you a big change in y. So the derivative there is large, the slope there is steep, whatever you want to say. It's very, the red curve is high sensitivity. The blue curve is low sensitivity, because sensitivity and steepness are 2 words for the same thing. So, with that in mind, we can now make our little model of the HPG system. And HPG, hypothalamus excites pituitary. Pituitary excites gonad, positive, positive. And then the important one is the gonad inhibits the hypothalamus. So we have a plus, plus, minus. We have a negative feedback loop. Now, the interesting thing about negative feedback loops is that if your LSF instructor has talked about this already, you know what I'm talking about. If not, they will. They talk about negative feedback loops as maintaining homeostasis. Don't they? And that's not wrong. I'm not saying that's wrong. But the LS7 instructor or the traditional physiology instructor is going to say, oh, body temperature is maintained at a constant rate by a negative feedback loop. It's just like the thermostat in the room. When your body gets hot, the hypothalamus senses the increased temperature and it sends out vasodilators. And the vasodilators put all that hot blood gets out into the extremities where it is easily radiated out into the air. So that cools you down. Conversely, if you're cold, hypothalamus puts out vasoconstrictors, and the vasoconstrictors keep the warm blood in the trunk where it's insulated and not in the hands and feet, which are little radiators that dissipate that blood, dissipate that heat, sorry. So there is the traditional rap about negative feedback loops promote homeostasis. So I just want you to hold that phrase right there. Just put a pin in that because I'm going to come back to that. So what we're going to do is make a differential equation model of this 3-variable system. And that's going to be H prime equals and P prime equals and G prime equals. And we said a lot of this is pretty trivial. Each hormone is going to degrade. Oh, just good old degradation. The pituitary is just going to respond to the hypothalamus directly. The gonad is just going to respond to the pituitary directly. And then the only question was, how do we fill in this thing, which is the negative feedback of G on H? But we answered that question. We know what that is. It's 1 over 1 plus G to the N. That's the negative feedback of the gonad on the hypothalamus. So we now have a little model. We have a differential equation. Well, we almost have a differential equation because I have not given you a value for n. We still have a parameter there. And the parameter is n. And it is very important that I have not given you a value for n. So first of all, these kinds of negative feedback loops are extremely common in endocrinology. Just as a little piece of endocrinology, it's not just the gonads that have these loops. You would have to include the thyroid. There's an HPT axis, hypothalamic pituitary thyroid, and these are thyroid hormones, and the thyroid hormones have negative feedback to the hypothalamus. This would also include the adrenal cortex. This would also include any organ that is under neural control, which are a lot. But that's taking me afield, so forget about that. So the next question is, how does the system behave? Now, by the way, just for a little fun fact for the men in the audience. Suppose you have a nice HPG system, which we all do, and you're a guy, you decide you want to bulk up a little bit. So you get a little, you go down to Venice Beach and you borrow somebody's needle, and don't take medical advice from me. You borrow somebody's needle, you buy some Dianabol or some synthetic testosterone, and you shoot up testosterone. So you now have the G is putting out testosterone if you're a male, and now you're going to have an exogenous source. So it's going to be, if this was the HPG axis for males, this could be in G, you could add a term called exogenous. And exogenous is whatever testosterone you are administering through the needle. Now, what is that differential equation? What does this system tell you? And well, actually, let me ask you a medical question. What is the primary medical presentation or primary symptom of a male who has been abusing testosterone or other anabolic steroids? What's the primary symptom, Alexa?
Stop producing testosterone.
Indeed, to put a name on it, the primary symptom is testicular atrophy. And if the guys are all doing this, the answer is yeah, that's what we're talking about. Why is that? Negative feedback system. What happens to your your thermostat controlled heater if you bring a very large hot object into the room? Answer, the heater shuts down. Doesn't it? Just saying. So this is a direct consequence. If you have a little exogenous testosterone, and you just call that an input of 1 or constant or whatever, that is going to result in a lower level of gonadal output, which is testicular atrophy. So negative feedback is a lot of fun. And it can return to bite you. But I want to get back to this question of negative feedback promotes homeostasis. It's just like the thermostat in your apartment. Because what I asked you to do for homework is to try a couple of different values of N. Shallow feedback, let's say N equals 3. And steep feedback, let's say N equals 9. And the answer is very, very different. And this is what you're going to do for homework for me, because this was the last homework assignment. What you're going to see, and I'll just tell you what you're going to see because I need you to produce this for me in simulation. When N equals, let's say, 2, what you will see, and now the question is, what am I going to plot? CoCalc can't plot 3D HPG axis, I don't believe. So let's just take 2 variables. Let's take H and G, let's say.
Actually, can. They should do it for their homework.
Can? Ooh, never mind. Who said no?
I've been getting errors.
So here's the HPG state space, positive only. And what you will see when N equals 2 is that no matter where you start, it spirals in to stable spiral, stable equilibrium point. Spirals into a stable equilibrium point. For those of you who are saying, are we ever going to see a spiral stable equilibrium point? Yeah, here's one. Here's one in 3D. And of course, I'm drawing it here flat on the page because I have a 2D page. But of course, this is going to be a trajectory in 3D. So, moral of story is that for a low n, that is to say for gentle feedback, negative feedback produces a stable equilibrium point. In other words, the people who are saying negative feedback promotes homeostasis, this is what they are talking about. Because homeostasis is a stable equilibrium point. And here it is. However, when n is equal to, let's say, 9, and certainly anything bigger than 9, what you are going to see is very, very different. What you are going to see is something you have never seen before. I will describe it. There is going to be a red trajectory, a red loop sitting in 3 space. And if you choose an initial condition, I don't care, right here, the trajectory out of that initial condition as you go to simulate it is going to go into the red loop and then basically merge with it. Now, when I say merge with it, it's going to merge with it on your computer screen because your computer screen only has 600 or 800 pixels vertically. In the math, where we have infinitely many pixels, the blue line never touches the red loop. It gets closer and closer and closer and closer. And as t goes to infinity, the blue trajectory approaches the red loop. So in the math, it never touches. It just gets closer and closer and closer and closer. But given our computer screens, within a few seconds in your simulation, it's going to look like it's on the red loop and just going around according to the red loop. Then the other part of the question was, okay, take a different initial condition. Let's take this initial condition. What's going to happen with that? Answer. It's going to zoom out, approach the red loop, and get closer and closer and closer and closer to the red loop. Until very quickly on your computer screen, it's going to look like it's on the red loop. Although again, in pure math, it's not. It's just getting closer and closer and closer. As a matter of fact, you take this initial condition and it goes right up to that red loop. And you take this initial condition and it goes right to that red loop. And you take this initial condition and it goes right to that red loop. Every initial condition in this space goes to the red loop when, for example, n is bigger than or equal to 9. Now, this is something you haven't ever seen before. Do you remember when we were talking about shark tuna? I said shark tuna is a bad model. People said, what do you mean it's a bad? Why are you teaching us bad models? And I said, one reason it's a bad model is if you have a different initial condition, you have a different trajectory. You remember shark tuna looks like this. Every initial condition is on its own little orbit. And I said, oh, that's a terrible model because for biology, because suppose this was body temperature and you had a fever one day. You have a fever one day, you're now on a different trajectory and you're going to stay on that trajectory forever. So this is a bad model. This is a great model because what this says is if you perturb off the behavior, it comes back. That's a big deal, and we saw that, of course, with equilibrium points. And the name for that is stable equilibrium point. Push it off, it comes back. Now we have an oscillation that has the same property. We've never had that before. An oscillation that has the property, if you push it off, it comes back. It's a robust oscillation. That is biology. So the only two things I want to say is number one, to this whole question of does negative feedback promote homeostasis or does negative feedback promote oscillation? We can now answer that question. And the answer is negative feedback with gentle feedback promotes homeostasis. Negative feedback with steep slope or highly sensitive negative feedback promotes oscillations.
We have a couple questions.
Yes.
What does this N thing represent?
The N thing, thank you for that call from Cincinnati. The N represents the steepness of the curve, right there. N equals 2 is gentle, N equals 3 is less gentle, N equals 9 is quite steep, N equals 20 is basically rectangular. It looks like that. It's indistinguishable from that. So it is the sensitivity of the system to the feedback equals the steepness of the slope of the feedback function. Does that answer?
I think so.
Good.
Second question, why does the blue line approach the red trajectory? Oh, wait, there was one more follow-up on that one. About the N. Does that mean in the neutral world, highly sensitive system will approach the trajectory?
Well, yes, if it's highly sensitive, then it will have this, that it's highly sensitive, that is N greater than or equal to 9. Then it will have this wonderful property that there is this single oscillation that everything zooms towards and is stable.
Other question. Why does the blue line approach the trajectory but never actually merge with it? Is it the nature of the system?
No, it's the nature of it's the nature of differential equations. Thank you for that question. The answer is the fundamental theorem on the existence and uniqueness of solutions to ordinary differential equations. That's easy for me to say, but the fundamental idea is determinism. One point has only one orbit. It's exactly the same as the question in a stable equilibrium point. You start from off the stable equilibrium point. Does the trajectory hit the stable equilibrium point? Does it actually coincide and hit it? Why not? Fundamental theorem on existence and uniqueness of solutions to ordinary differential equations. Even in the stable equilibrium, the trajectory gets closer and closer and closer, but it cannot touch the equilibrium point because there is already an orbit there. The orbit that is the one point, which is I'm at the equilibrium point. If another orbit crossed the equilibrium point, you'd have two orbits at that equilibrium point, violation. So it does indeed get closer and closer, and in the math, it gets closer and closer. In practical life and on your computer screen, it's there. So to go back to the homeostasis thing, which is very interesting, we can now give a really good answer to the homeostasis question, which is gentle negative feedback promotes homeostasis, stable equilibrium point. Steep negative feedback, highly sensitive negative feedback promotes oscillations. The example that I like to use is think about a parent teaching a kid how to drive. So the kid is trying to maintain down the center line, trying to maintain equilibrium down the center line. And the parent is giving corrective feedback. So now if you imagine a nice mellow parent, the kid is drifted to the left. The parent says, okay, you're drifting to the left, now correct right a little bit. That kid is going to maintain an approximate equilibrium down the center line of the lane. Now imagine a hypersensitive parent. You're going too far to the left, correct right. You're going too far to the right, correct left. What is the trajectory of the car going to be? Everyone in the room here is doing this, exactly. Moral of story, steep negative feedback promotes oscillation. And that would be an example of that. So then there's really only one other point that I want to make, which is going back to this red loop. What the heck is this red? This red loop is a major thing, a major thing. And the question is, what is it? So we already said it's kind of like a stable equilibrium in the sense that if you push the point off it, it comes back. It is stable, but it's not a stable equilibrium point. It's a stable. These red loops are called limit cycles. Just like if it's an equilibrium point, it's called a limit point. This is called a limit cycle. And this is a stable. The red loop that I drew there, and that happens in the HPG system, that is a stable limit cycle, also known as a stable oscillation. So just kind of like meditate on that phrase, stable oscillation. That's a little bit of conflict in terms, stable oscillation. If I tell you something is oscillating, you don't think of it as stable. Stable oscillating, you think about, you know, oscillations in a relationship or oscillations in the control of a vehicle, or oscillations in the operation of a machine. Those are all bad. And those are all called instabilities. Because in many people's minds, oscillation means instability, right? If you and I are in a relationship and we're constantly oscillating in our affection for each other, that's called instability. That's bad. This is something very different. This is a stable oscillation, which means that it's a kind of a stable instability, if you will. And we have to sort of scratch our heads a little bit and think about this object because it is such an interesting and important object for biology. Is this concept of a stable limit cycle. So now the last thing I want to do is just give you one piece of terminology, and then we are have totally covered 4.1. And that is this. I want to take that analogy with the equilibrium point, the stable and unstable equilibrium points. And I want to take that very seriously. And I'm now going to define, I'm going to make a definition. I'm going to define an attractor of a dynamical system. So an attractor is a subset A of state space such that for a neighborhood of initial conditions, I'm going to call that neighborhood N, a neighborhood N of initial conditions, every state point X in N has X approaches A as T approaches infinity. So let's just kind of stare at that for a second. What is this saying? It's saying an attractor is a subset of state space that sucks points. One of the exercises says, is this like a black hole? This is like a black hole. An attractor is a set that sucks nearby points, that attracts nearby points in its basin. So we're now going to extend the word basin. So now just not equilibrium points have basins, but stable limit cycles have basins too. And the basin of this red loop is the whole space minus one mathematical point, which is the unstable equilibrium point at the center of all of this. Because there is an unstable equilibrium there. So the basin here is the whole space except that unstable equilibrium point. So now, here's our definition: a subset of state space that sucks points. Can you give me an example of an attractor that we have seen already weeks ago? Well, what about a stable equilibrium point? Let's stare at the definition. Is a stable equilibrium point a subset of state space? Yes. Does it have a neighborhood of initial conditions such that every point in that neighborhood goes to that point as t approaches infinity? Oh, yes. Oh, yes. That's called the basin. So a stable equilibrium point is now going to get retro-named. It's going to get a second name. And its second name is going to be point attractor. So that's just definition. Point attractor is a stable equilibrium point. But now that I have the concept of attractor, I can now have my second type of attractor, which I can now say a stable oscillation is equal to a limit cycle attractor. And so now we have the concept of a limit cycle attractor. This is a second kind of attractor. There is a third. We'll talk about it in a month. But right now there's two. Point attractor, which is equilibrium, and limit cycle attractor, which is robust and stable oscillation, which is going to turn out to be very important in biology. Last thing I want to say before I ride off into the sunset is we said when we started to talk about this that the concept of homeostasis was an attempt to capture the notion of equilibrium in the scientific sense, not in the mathematical sense. Of course, we know what it is in the mathematical sense, but then we deal with all of these situations in chemistry and physiology where they want to talk about the notion of equilibrium. And they have this doctrine of homeostasis, which says stable equilibrium. But then I showed you all of this data that say it's not an equilibrium. It's an oscillation. Now we can have a scientific concept which will take us beyond homeostasis, because now we can say we don't want our phenomena to be governed by stable equilibrium points like in homeostasis. We now have the concept of dynamic equilibrium. And dynamic equilibrium means limit cycle attractor. And so just to close, stable EP equals homeostasis. Stable limit cycle attractor equals, I don't know what you want to call it, homeodynamics. So if the challenge was, if you're going to take away our concept of homeostasis, Alan, as you're threatening to, what are you going to put in its place? There was something right about homeostasis. We kept saying, keep the homeo, lose the stasis. Well, here it is. This keeps the homeo because it's stable and attracting, and it loses the stasis. Thank you very much.
Is that homeostasis dynamics?
I call that homeodynamics. That's my word. I have no idea what to call it. So we're going to post this. Right side, you get all that? And I'll see you on. No, I'll see you on Monday.
Monday. Review session.
And if so, in like what way?
What I what?
Is this going to be on the final? And if so,
Could be.
what kind of questions?
This was very high level. So it would be, well, I mean, say this. HPG model on the final, yes. Behavior of the HPG on model on the final, low end, high end, yes. Philosophical rumination about equilibrium and oscillation, maybe. Idea of an attractor, yes. See you at the review session on Monday.
Have you announced the time?
6.
Where?
Do we know where?
Yes. Didn't I send it to you? It's in Broad,
It's in Broad. Oh,
Broad something or other.
the giant lecture hall.
Yeah.
Oh yeah, and we have homework 9 that's all online. When is that?
And that's due Monday as well.
He said he would go
Wait,
over
did
the
you say that you had All-Stars tomorrow?
I could.
Oh, okay. I was like, you sent an email.
Yeah. Yeah, I did. I'm also holding office hours tomorrow afternoon if people are around. I got to give a talk to the LS people about LS30 tomorrow at 2, if any of you want to come to that. No, we don't want them there?
I
Okay.
think it might inhibit a discussion with the instructors.
Okay. Okay.
Thank you.
Selected people may come. Thank you, guys. Thank you, Alex.
Thank you.
You got lots of thanks, Alan. We'll see you next quarter. Thank you.
Aw.
Thank you.
Yeah.
Okay. Just to clarify, attractor is just another word for stable equilibrium point. This just adds the concept of stable oscillation too.
No. Point attractor is another name for stable equilibrium point. But attractor now comes in at least 2 flavors. Number 1 is point, and number 2 is limit cycle oscillation. 2 kinds of attractors.
You know the lecture hall?
Bless you.